Okay, let's unpack this. You've given us a stack of material diving deep into one of the most transformative stories in human history. How we went from, well, not even knowing nuclear energy existed to unleashing its incredible power.
Yeah, and we're mostly drawing from Isaac Asimov's Worlds Within Worlds. It's a great guide for this.
It really is. Asimov, he kind of sets the scene perfectly, doesn't he?
Hmm.
Reminds us how much changed in the couple of centuries before the 1900s, steam engines, railroads, cars.
Planes, radio, TV. I mean, just an astonishing age of technological leaps.
Right. You'd think maybe that was it. We'd sort of peaked. But he says the stuff starting around, what, 1939 with the atom. That felt quite so fantastic, quite so unbelievable.
And the reason's pretty straightforward, really. Suddenly you had possibilities that, well, they sounded like pure science fiction.
Inexhaustible energy, new worlds, ever-widening knowledge.
Exactly. It all suddenly seemed, graspable, within reach.
And it's kind of wild when you stop and think that nuclear energy has actually been powering things for us all along.
Oh, absolutely. The sun, right. That's the ultimate example. A vast nuclear engine, as Asimov puts it, billions of years old, just bathing us in energy.
Life wouldn't exist without it. We've
Yeah.
basically been living off nuclear energy from space forever.
Mm-hmm. But the story we're getting into today, based on these sources, it's about how we humans learn to produce and control it ourselves here on Earth.
Right. And Asimov shows it wasn't just one moment.
Not at all. It needed three seemingly separate threads of science to kind of weave together. You had owls, you had electricity, and you had energy itself.
So that's our mission for this deep dive then. Follow those threads. See how scientists piece together all these clues about reality itself.
Yeah, leading them to crack open the secrets of the atom's nucleus.
Yeah.
Through, radioactivity, fission, the bomb.
Reactors, the hunt for fusion. It's really a shortcut to understanding one of the biggest turning points in modern history. Ready to jump in?
Let's do it.
Okay, thread number 1, the atom. Before all this subatomic stuff, what was the picture? What did scientists think matter was made of?
Well, the basic idea of atoms, these tiny building blocks, it goes way back. But it was John Dalton, early 1800s, who really put it on a scientific footing.
How'd he do that?
By looking really carefully at how elements combined in chemical reactions, ratios.
And that let him figure out relative atomic weights, right?
Yeah.
Comparing elements.
Exactly. Like, okay, if water is made of hydrogen and oxygen in this ratio and you use this much of each, you can work out how heavy an oxygen atom is compared to a hydrogen atom.
It started with hydrogen as 1, oxygen as 8, something like that.
Yeah, initially. They corrected oxygen to 16 later, based on better data about water.
And others, like Berzelius, kept refining this system using that oxygen 16 standard.
Right. And for a lot of elements, these atomic weights turned out pretty close to whole numbers. Aluminum around 27, gold near 197. Look neat.
But here's the catch. The thing that puzzled chemists back then, some elements just didn't fit.
Exactly. Chlorine was always around 35.5, iron like 55.8.
Why wasn't it a whole number if atoms were these fundamental identical units for each element?
That was the mystery. It was a real head scratcher. It suggested, maybe things were more complicated than they thought. Something else was going on.
So while chemists are wrestling with these weights, physics is having its own revolution with electricity. How did those worlds start to connect?
Well, the link started to show up when people began passing electricity through liquids. Michael Faraday, this is way back in 1832.
Wow, that early.
Yeah. He found electricity could make atoms, or groups of atoms, he called them ions, move through solutions.
Ions, just charged atoms, basically.
Pretty much, yeah. Gained or lost an electron. And Faraday noticed something really key. To move or deposit a specific number of atoms for lots of different elements, you always needed the exact same amount of electricity.
Like electricity came in little packets tied to atoms somehow.
Precisely. A huge hint that electricity itself was fundamental. It came in discrete units.
And eventually someone gave this unit a name.
Yep. George John Stone, Stoney, 1891, suggested calling it the electron, but actually seeing it or working with it directly, that was tricky.
Until the vacuum tube experiments.
Exactly. Those experiments really took off.
Cathode rays. You pump the air out of a tube, crank up the voltage.
Right, like those Geissler tubes from the 1850s, you'd get these glowing rays shooting from the negative end, the cathode. And the big question was, what are they? Waves? Or particles?
Crookes' experiments started pointing towards particles, didn't they?
They did, yeah. In the 1880s, he showed these cathode rays could actually turn a tiny paddle wheel inside the tube.
Meaning they had mass, momentum.
Right. And crucially, they were bent by a magnet, which meant they had an electric charge.
But J.J. Thomson, in 1897, he's the one who really nailed it down.
Thomson did these really careful measurements, how much the rays bent in electric fields, magnetic fields. He confirmed they were streams of particles.
The electrons.
The electron stone he had named. But Thomson showed they were incredibly light, much lighter than any atom, and negatively charged. It was basically the discovery of the first subatomic particle.
Wow, so atoms aren't the bottom level after all. There's smaller stuff inside.
Exactly. An electric current. That's just these tiny electrons moving around. That was the picture starting to form. Matter made of atoms, probably positive somehow, and these tiny, light, negative electrons that could be detached.
Okay, so we've got atoms, we've got electrons. How did they slam together in this story? It seems like it came from an unexpected direction.
Totally unexpected. Came from a brand new phenomenon. In 1895, Wilhelm Röntgen stumbled onto X-rays coming from his cathode ray tubes.
Right, those invisible penetrating rays.
Yeah, and that got everyone wondering if there were other kinds of invisible rays out there.
And Henri Becquerel was looking into this, with stuff that glowed after being exposed to light.
Exactly. He was studying a uranium salt potassium uranyl sulfate. He thought maybe its glow was related to X-rays.
But then he found something else entirely.
He did. The story goes he left some of the salt on a photographic plate, wrapped in black paper, stuck it in a drawer, no sunlight involved, and the plate still got exposed. Fogged up.
Whoa. Just from the uranium salt sitting there in the dark.
Yeah. He realized the uranium itself must be continuously emitting some kind of powerful, penetrating radiation all on its own. No external energy needed.
That's incredible. Energy just pouring out of a rock, seemingly forever.
It was completely unprecedented. Nobody had seen anything like it.
And Marie Curie picked up on this.
She did in 1898. Her work was crucial. She showed it wasn't about the specific chemical compound, it was the uranium atom itself that was responsible. She's the one who coined the term radioactivity.
And uranium was the heaviest element they knew back then, right? Number 92.
Yep. Thorium, number 90, was soon found to be radioactive too. It seemed linked to these really heavy elements.
And they quickly realized this radiation wasn't just one single thing either.
No. When they passed the radiation through a magnetic field, it split into 3 distinct types.
Alpha, beta, gamma.
That's right. Alpha rays bent one way, suggesting a positive charge. Beta rays bent the other way, much more sharply, suggesting a negative charge and less mass. And gamma rays went straight through, like light neutral.
And the beta particles? They turned out to be electrons, didn't they?
Exactly. Becquerel himself showed that in 1900. So you had electrons not just flowing in wires or being knocked off atoms by light, which Thomson had also shown, but actually being shot out from inside radioactive atoms.
So radioactivity meant atoms weren't stable, unchanging things. They could actually transform internally.
Precisely. It was becoming undeniable that electrons were part of atoms and that atoms could change. This completely forced a rethink of the atom's internal structure.
Which brings us to Ernest Rutherford.
Ah, yes, Rutherford, and his absolutely landmark gold foil experiment.
This is his famous one, right? Where he shot particles at gold foil.
Alpha particles, yeah, which they knew were positive. He shot them at this incredibly thin sheet of gold foil.
And most went straight through. But some bounced off. He said it was like firing a cannonball at tissue paper and having it bounce back.
That's the famous quote. It was astonishing. Most zipped through, meaning the atom was mostly empty space. But a tiny fraction were deflected at huge angles. Some even came straight back.
Which completely blew up the old plum pudding model, where electrons were just scattered in a positive blob.
Totally demolished it. Rutherford realized the only way to explain this was if the atom's positive charge and almost all its mass was concentrated in an incredibly tiny dense core at the center.
The nucleus.
The nucleus. Positively charged, deflecting those positive alpha particles, the electrons must be orbiting way out, leaving most of the atom empty.
And this model also explained Faraday's ions, right? Atoms gaining or losing those outer electrons.
Exactly. And it turned out those alpha particles Rutherford was using, they were probably helium nuclei, just the bare nucleus stripped of electrons.
Okay, so Rutherford gives us the nuclear model. Meanwhile, other clues about the nucleus were popping up.
Right. Charles Barklow was doing experiments bombarding elements with X-rays. He found that each element, when hit, emitted its own characteristic X-rays. Unique signature X-rays.
Like a fingerprint for each element.
Kind of, yeah. Each element's X-rays had a different penetrating power.
And then Henry Moseley took that discovery and ran with it.
He did. Brilliant young guy. Working with Barklay's results around 1913, Moseley measured the exact wavelengths of these characteristic X-rays for element after element.
And he found a pattern.
A beautiful, perfect pattern. He found he could arrange the elements in order based on these X-ray wavelengths, and that order corresponded directly to the amount of positive charge on the nucleus.
So not atomic weight, but the charge on the nucleus was the fundamental thing defining an element.
Precisely. He called it the atomic number.
Mm-hmm.
This became the defining characteristic. Hydrogen is 1, helium is 2, oxygen 8, uranium 92. Bohr's new atomic theory supported this too. It finally cleared up what made an element an element.
Okay, but wait. If atomic number, the number of positive charges, which we now call protons, defines the element, why do we still have that old problem, the non-whole number atomic weights?
Right. If all chlorine atoms have 17 protons, atomic number 17, why isn't its weight exactly, say, 35 times hydrogen's weight or something neat like that? Why 35.5?
It seems like the atomic number should fix the weight too.
You'd think so. But this is where the final piece of the basic atomic structure puzzle clicked into place. Isotopes.
Isotopes. Yeah.
Remember Dalton's assumption that all atoms of a given element were identical in every way, including mass. Radioactivity started showing that wasn't quite right.
How so?
Well, scientists studying those long radioactive decay chains, like uranium decaying through many steps eventually to defeat this. Lead noticed something funny. Lead produced from uranium decay seemed chemically identical to ordinary lead, but it had a slightly different atomic weight than lead from, say, thorium decay.
Same element lead, but different weights.
Exactly. And Frederick Soddy put his finger on it.
What was his insight?
Soddy realized that atoms of the same element, meaning they have the same atomic number, same chemical properties, could actually have different masses. He coined the term isotopes.
Meaning same place in the periodic table, right?
Yeah.
Because chemically they're the same.
Precisely. He pointed to examples where a radioactive substance behaved chemically just like thorium, but had a totally different mass and radioactive half-life. Same element, different versions.
And J.J. Thomson, the electron discoverer, he proved this wasn't just some weird radioactivity thing.
Right. He built an early version of a mass spectrometer, used magnetic and electric fields to bend beams of ions. Heavier ions bend less, lighter ones bend more.
So he could separate atoms by mass?
Yes. And when he ran ordinary neon gas through it, neon's measured atomic weight was about 20.2. He found the beam split into two.
Two types of neon.
Yep, one corresponding to a mass number of 20 and a fainter one corresponding to mass number 22. Ordinary neon gas was actually a mixture, mostly neon 20 with a bit of neon 22. The 20.2 was just the average weight based on their natural abundance, about 90% and 10%.
So that's it. Those weird fractional atomic weights were just averages of different isotopes mixed together.
Exactly. Francis Aston built much more precise mass spectrometers after World War I and confirmed this was super common. Chlorine's 35.5. It's a mix of chlorine 35 and chlorine 37, about 3/4 Cl35, 1/4 Cl37.
So some elements have only one stable isotope, like fluorine-19, but most are mixtures.
That's right. Carbon is mostly carbon-12, but has some carbon-13. Nitrogen is N14 and N15. Oxygen is mostly O16, but has tiny bits of O17 and O18. Even hydrogen has hydrogen-1 and the heavier hydrogen-2, deuterium.
And crucially for our story, uranium exists as different isotopes too.
Yes.
Yeah.
Mostly uranium-238, but about 0.7% is the slightly lighter uranium-235. And as we'll see, that small difference in mass, just 3 neutrons, makes a world of difference when it comes to nuclear energy. Isotopes are key.
Okay, incredible. So we've got the atom figured out, nucleus with protons and neutrons, electrons orbiting, different isotopes. We've got electricity as electron flow. Let's bring in the third thread, energy. What's the basic idea there?
Well, energy in physics is basically the capacity to do work, to make something happen, move something against a force. And it comes in loads of forms, right? Motion, heat, light, electricity, chemical bonds.
And just like with matter, scientists were hunting for conservation laws. Lavoisier nailed down conservation of mass in the 1770s. Mass isn't created or destroyed in chemical reactions.
Right. That was bedrock for 19th century chemistry. Energy conservation was trickier because energy changes form so easily, it's hard to track.
But James Joule, in the 1840s, he showed connections.
He did. He showed you could convert, say, mechanical work directly into heat, and there was a fixed exchange rate. A certain amount of work always generated the same amount of heat.
Connecting different forms of energy.
Exactly.
Yeah.
And then Hermann von Helmholtz in 1847 pulled it all together into the law of conservation of energy. The total energy in a closed system is constant. It just changes form.
Another bedrock principle. So if energy is conserved, where does the energy for, say, a fire come from? People understood chemical energy, right?
Yes. Chemical energy is all about the bonds holding atoms together in molecules. It takes energy to break those bonds.
But you get energy back when new bonds form.
Right. And if the new bonds formed are stronger, more stable than the old bonds you broke, then overall energy is released.
Like burning hydrogen and oxygen to make water. You break HHH and OO bonds.
Takes energy, but then you form strong OH bonds in water, and that releases more energy than you put in. The difference comes out as heat and light. That's combustion.
And burning is a classic example of a chain reaction, isn't it, in chemistry?
Oh, absolutely. The heat released by one bit burning ignites the fuel next to it, which burns and releases heat, igniting the next bit. A lit match starts the paper burning, the paper ignites the wood, the fire spreads. That's a chemical chain reaction.
And this understanding was tied to those outer electrons, right? Sharing or transferring them to make bonds.
Yes, people like Abegg and Lewis figured out that chemical bonding was about electron behavior. Chemical energy changes were due to shifts in these outer electrons.
Okay, so chemical energy explained fire, engines, even biology pretty well. But it ran into a massive wall when scientists looked up at the sun.
Yeah, this was maybe the biggest scientific headache of the late 19th century. Where does the sun get all its energy? It's been shining for, well, seemingly forever.
They knew chemical burning was out. Calculations showed the sun would burn out in like 1,500 years if it was just a giant lump of coal.
Ridiculously short time frame. So Helmholtz came up with another idea. Gravitational contraction. The sun slowly shrinking under its own weight, converting potential energy into heat and light.
Which fits the conservation of energy principle.
It does. But when they calculated how long that could power the sun, the answer was still only about 25 million years. Tops.
And by then, geologists and biologists were saying, hang on, the Earth, life, it's way, way older than that. Hundreds of millions, maybe billions of years old.
So you had this huge contradiction. Either conservation of energy was wrong, or the Earth's age was wrong, or there had to be some completely new, incredibly powerful energy source nobody knew about yet.
A massive puzzle. And then along comes Becquerel in 1896, finding rocks that just glowed on their own, radioactivity.
Exactly. This offered a potential way out.
How could a faint glow from a rock solve the sun's energy crisis?
Well, they found radioactive decay releases the kinetic energy of the alpha and beta particles, the energy of the gamma rays.
But surely not much energy compared to the sun.
Per second, from a small sample, no. But here's the absolute key. It's relentless. It keeps going. Uranium decays, yes, but its half-life is 4.5 billion years.
So while the power output at any instant is small, the total energy released over those immense timescales is gigantic.
Vastly more energy, gram for gram, than you could ever get from chemical burning. Suddenly, here was a candidate for a long-lasting, incredibly potent energy source hidden inside matter itself.
Becquerel and Rutherford quickly jumped on this idea.
They did. They started talking about atomic energy, some huge reservoir inside the atom that was slowly leaking out in radioactive elements.
And Rutherford's nuclear model gave it a specific location.
Right. Chemical energy was about outer electrons. This new, immense energy had to be coming from that tiny, dense nucleus he'd discovered. So really, the proper name wasn't just atomic energy, it was nuclear energy.
And this finally gave a plausible explanation for the sun's longevity. It wasn't burning coal or just shrinking. It was tapping this nuclear energy.
It was the first real scientific candidate that fit the timescales.
Okay, so we know where the energy is, the nucleus. But why is there so much of it? Why is nuclear energy so vastly greater than chemical energy?
For that, we need Einstein and his most famous equation.
EMC, sure. Mass energy equivalence.
Exactly. Coming out of his 1905 theory of special relativity, which itself was sparked by things like the Michelson-Morley experiment showing the speed of light is constant, Einstein realized something profound. Energy, E, and mass, M, aren't separate things that are conserved independently. They're fundamentally interchangeable.
Two sides of the same coin.
Sort of, yeah. And they're linked by the speed of light squared, SU.
And C, the speed of light, is a huge number. So C squared is astronomical.
Staggeringly huge, which means even a minuscule amount of mass is equivalent to an absolutely enormous amount of energy. The source says 1 gram of mass equals 900 billion ergs of energy. It's hard to even grasp.
So wait, when you burn hydrogen and make water, and energy is released, does the water actually weigh less than the hydrogen and oxygen you started with?
Yes, but by an incredibly tiny amount, maybe millionths of a gram. Far too small for Lavoisier or any 19th century chemist to measure. That's why conservation of mass seemed perfectly true for chemistry.
But in radioactive decay, where the energy release per atom is much, much bigger.
The corresponding mass loss is also bigger. Still tiny, but big enough that eventually it could be measured. And when they did the calculations, the measured energy released matched the calculated mass lost exactly, according to Eamon Sawant.
Wow. So the old laws weren't wrong, just incomplete. The real law is conservation of mass energy.
Precisely. Mass is just an incredibly concentrated form of energy. This is the ultimate source of the vast energy locked within the nucleus. It's the energy equivalent of the tiny bit of mass that disappears the mass defect when protons and neutrons bind together. That's the binding energy.
And nuclear reactions release energy by rearranging nucleons into states with slightly less total mass, converting that missing mass into energy.
You got it. That's the fundamental source.
Okay, we understand the why now, mass conversion. We know the nucleus has protons and neutrons. How do we actually trigger these nuclear reactions? How do we tap into that energy store?
Well, the first attempts involved basically throwing things at the nucleus, bombardment, using high-energy particles like alpha particles or protons.
But the nucleus is positive, and so are alphas and protons. They repel each other.
Fiercely. And the nucleus is a minuscule target, so you needed to accelerate your projectiles to incredibly high energies to overcome that repulsion and have even a tiny chance of scoring a direct hit.
Using particle accelerators, like the Cockcroft-Walton machine or Lorenz's cyclotron?
Right. They managed to cause some artificial nuclear reactions, transmutations, but it was incredibly inefficient. The source uses Rutherford's analogy, like trying to light a candle using 300,000 randomly thrown matches.
You put vastly more energy into accelerating the particles than you ever got out from the rare reaction.
Exactly. Which is why Rutherford himself was famously pessimistic about ever getting practical energy from the atom. He thought it was moonshine.
But then came the discovery that changed everything for bombardment.
The neutron. Chadwick's discovery in 1932.
The neutral particle. No electric charge.
Which means it isn't repelled by the positive nucleus. A neutron can just wander right up to a nucleus, even a slow-moving one, and potentially be absorbed. Suddenly, hitting the target became much, much easier.
A real game changer for inducing nuclear reactions.
Absolutely. And then Enrico Fermi in 1934 made another critical discovery working with neutrons.
What was that?
He found that, counterintuitively, slow neutrons were often more likely to be captured by a nucleus than fast ones.
Slower is better. Why?
Yeah. Think of it like the neutron spending more time near the nucleus as it drifts by slowly, giving the nuclear forces a better chance to grab it. It effectively has a larger target area, what physicists call a larger nuclear cross-section, for slow neutrons.
And you could slow down fast neutrons.
Yeah, by having them bounce off light atomic nuclei like hydrogen in paraffin wax, or deuterium in heavy water, or carbon in graphite. These materials are called moderators.
So using neutrons, especially slow neutrons, made nuclear reactions much more efficient to trigger. But you still needed to produce those neutrons in the first place, which took energy. Rutherford's pessimism wasn't quite dead yet.
Not quite. Until the next truly revolutionary discovery. Something utterly unexpected happened when neutrons hit the heaviest nuclei.
Fission.
Nuclear fission. Before this, when a nucleus absorbed a neutron, it usually just became a heavier isotope of the same element, or maybe beta decayed into the next element up.
Like Fermi was trying to do in 34, hitting uranium, element 92, hoping to make element 93.
Right. He didn't identify element 93 then, though his work eventually led to neptunium-93 and plutonium-94 being made from U-238 later on. But he got really strange results he couldn't explain. Other groups did too.
And the breakthrough came from chemists trying to identify these strange products.
Yes. Otto Hahn and Fritz Strassmann in Berlin, working with Lise Meitner, though she'd had to flee Germany by then. In late 1938, they were meticulously analyzing what happened when uranium was bombarded with neutrons, and they kept finding barium.
Barium, element 56. How on earth do you get barium from uranium, element 92? That's like halfway down the periodic table.
It seemed absolutely impossible by any known nuclear process. Hahn was baffled, wrote to Meitner about these bursting results.
And Meitner, with her nephew Otto Frisch, Figured it out over Christmas break 1938.
They did. They realized the uranium nucleus wasn't just chipping off a small piece, it was splitting, breaking into two roughly equal lighter nuclei, like barium and krypton, element 36. 56 plus 36 was 92.
It was actually splitting in half.
Yes. They pictured the large uranium nucleus like a wobbly liquid drop. Absorbing a neutron made it wobble violently. The electrical repulsion between all the protons pushed the two emerging halves apart, overcoming the strong nuclear force holding it together. It split.
And they called it fission, borrowing the term from biology for cell division.
Frisch suggested the name, yeah. And the crucial thing they calculated was that this fission process would release a truly enormous amount of energy per nucleus. Way more than any radioactive decay or simple transmutation, about 10 times more.
Wow. Okay, huge energy release.
Yeah.
But still, if it's just one neutron and causing one split...
Right. It's still not a self-sustaining energy source. You're still putting neutrons in. The final critical piece was needed.
It's a chain reaction concept.
Exactly. The idea that a nuclear reaction could trigger more nuclear reaction.
And Leo Szilard had actually thought about this years earlier.
He had. Remarkably, back in 1933-34, reading about Rutherford's pessimism, Szilard had the insight. What if you could find a nuclear reaction that, when triggered by one neutron, released more than one neutron as a product?
Those newly released neutrons could then trigger more reactions.
Which would release more neutrons, triggering even more reactions, a self-sustaining chain reaction. He even patented the idea, though he couldn't point to a specific reaction that would work.
Until fission was discovered. Did fission release extra neutrons?
That was the multi-billion-dollar question in early 1939, and experiments very quickly confirmed, yes. When a uranium nucleus, specifically U-235, fissions, it doesn't just split and release energy, it also kicks out, on average, about 2 or 3 new fast-moving neutrons.
There it is. That's the key.
That's the absolute key. One slow neutron goes in, causes a U-235 nucleus to split, releasing a huge amount of energy, and 2 or 3 more neutrons.
Which can then, potentially, go on to hit 2 or 3 other U-235 nuclei, causing them to fission, releasing more energy and even more neutrons.
Exactly, an exponentially growing cascade, a nuclear chain reaction.
Suddenly, the possibility of releasing the energy from a large amount of uranium, triggered by just a single neutron, became terrifyingly real.
The numbers were staggering. Complete fission of 1 gram of U-235 releases as much energy as burning about 3 tons of coal. And it could happen almost instantaneously.
Szilard must have been horrified and vindicated at the same time. He saw the bomb potential immediately.
He did. Deeply worried about Nazi Germany getting there first, he, along with Wigner and Teller, persuaded Albert Einstein, the most famous scientist in the world, to sign a letter to President Roosevelt in August 1939.
Warning him about fission and the potential for extremely powerful bombs of a new type.
Yes, that letter was a major impetus for the U.S. government to start seriously investigating, eventually leading to the Manhattan Project.
But going from the idea of a chain reaction to a working bomb, that wasn't easy.
Oh, incredibly difficult. Huge scientific and engineering hurdles. One major one was getting enough fissionable material together. You need a certain amount, a critical mass, or critical size.
Why? What does critical mean here?
It means you need the lump of fissionable material to be large enough so that, on average, at least 1 neutron from each fission goes on to cause another fission within the lump before it escapes out the size or gets absorbed by something non-fissionable. If you produce neutrons faster than you lose them, the reaction grows supercritical. If you lose them faster, it dies out subcritical. Critical is the break-even point.
And this is where the isotopes became absolutely crucial again.
Yes. Niels Bohr, another giant of physics, made a key theoretical contribution. He realized that it was the rare uranium-235 isotope, only 0.7% of natural uranium, that was easily fissioned by slow neutrons.
What about the common U-238?
U-238 mostly just absorbs neutrons, especially faster ones, without fissioning. It acts like a poison, soaking up neutrons needed to sustain the chain reaction in U-235.
So natural uranium wouldn't work easily for a bomb.
Not easily. You'd need a huge amount, and likely a moderator. For a bomb, you needed to solve this U-238 problem. 2 main paths emerged.
Enrichment, separating the U-235.
Exactly. A fiendishly difficult task since isotopes are chemically identical. But if you could enrich the uranium, get mostly U-235, the critical mass needed becomes much smaller. This was the path taken for the Hiroshima bomb.
Now the other path.
Use the neutrons absorbed by U-238. It turns out U-238 absorbing a neutron doesn't fission, but through a couple of radioactive decays, it transforms into a new element, plutonium-239. And plutonium-239 is readily fissionable, similar to U-235.
So you could build a reactor using natural uranium and a moderator, let the U-238 absorb neutrons, and then chemically separate out the plutonium produced.
Precisely. This was the path for the Nagasaki bomb.
But first they had to prove a controlled chain reaction was even possible.
Yes. And that was achieved by Fermi's team at the University of Chicago, under the stands of the old football field, Stagg Field.
The Chicago Pile 1, December 2nd, 1942.
They built this huge pile, literally layers of graphite blocks, the moderator, with lumps of natural uranium oxide embedded in it. And it had control rods made of cadmium, which absorbs neutrons very strongly.
So they slowly pulled out the control rods,
allowing more and more neutrons to find U-235 instead of being absorbed by the cadmium, until at a calculated point, the pile went critical. It sustained a chain reaction, producing energy, controllable by moving the rods in or out.
The first artificial nuclear reactor. Rutherford's pessimism was finally definitively overcome.
It was a pivotal moment. Controlled nuclear energy was real.
And a bomb followed soon after. An uncontrolled chain reaction.
Yes. The designs involved achieving supercriticality extremely rapidly, either by slamming two subcritical pieces of enriched uranium together, the gun-type design, or by using conventional explosives to crush a subcritical sphere of plutonium into a dense supercritical state, the implosion design.
The Trinity test in New Mexico, July 16, 1945, proved the implosion design worked.
A terrifying success. And then, just weeks later, the wartime use. Hiroshima on August 6th, Nagasaki on August 9th.
Bringing World War II to an end, but ushering in the nuclear age, with all its fear and potential.
Absolutely. It reshaped global power dynamics overnight. Other nations raced to develop their own weapons. Thousands of tests followed over the decades, although, thankfully, 1945 remains the only time they've been used in war.
The source mentions people even thought about non-military uses for nuclear explosives back then, like digging harbors.
Yeah, there were ideas floated for peaceful nuclear explosions, massive earth-moving projects, resource extraction. Most of those ideas didn't pan out due to radiation concerns, obviously.
So fission was harnessed, destructively, but also with the potential for controlled power. What happened on the controlled side after Fermi's pile?
Well, the immediate focus was military, but peaceful applications followed. Controlled chain reactions are the heart of nuclear reactors for generating useful power.
Like powering submarines.
That was one of the first big successes. The USS Nautilus, 1954. Nuclear power gave submarines unprecedented underwater endurance and speed. Changed naval warfare. Now it's standard for subs, aircraft carriers.
And generating electricity for civilians.
That came quickly, too. The Soviets connected a small reactor to the grid in 1954. The UK opened Calder Hall, the first commercial-scale plant, in 1956. The US followed with Shippingport in 1957. The era of nuclear power plants began.
Now, you mentioned plutonium being created from U-238. That leads to the idea of breeder reactors, right? Making more fuel.
Yes, this is a really important concept for the long-term potential of fission. Remember, natural uranium is mostly non-fissionable U-238, but U-238 can absorb a neutron and become fissionable Pu-239.
So a breeder reactor is designed to do both. Sustain a fission chain reaction and convert U-238 into Pu-239.
Exactly, and potentially create more new fissionable fuel, Pu-239, than the original fissionable fuel, U-235 or Pu-239. It consumes, it breeds fuel.
Which would mean you could eventually use almost all the uranium, not just the 0.7% U-235.
Right, and potentially thorium too,
Okay.
which can be converted into fissionable uranium-233. If breeder reactors could be perfected and deployed widely, it would turn nuclear fission into an energy resource potentially 100 times larger than all coal and oil combined. Truly vast.
But there are challenges with breeders, and a big challenge with all fission power: the waste.
Absolutely. The fission products, the leftover fragments like barium and krypton and many others, are intensely radioactive. Some remain hazardous for thousands, even hundreds of thousands of years. Finding safe, permanent disposal solutions for this high-level nuclear waste is arguably the biggest hurdle for fission energy.
Okay, so that's fission splitting heavy atoms.
Right.
But there's the other side of the nuclear coin, the energy source of the sun: fusion.
Right, fusion. Joining light nuclei together like hydrogen isotopes to form heavier ones, like helium.
And this releases even more energy per unit of mass than fission.
Potentially, yes. Maybe 15 times more energy per gram of fuel compared to uranium fission. And again, it works by converting a tiny bit of mass into energy, according to Imsiaport. The resulting helium nucleus weighs slightly less than the hydrogen isotopes that went into it.
Astronomers figured out pretty early on that the sun must run on something like this.
Yeah. Eddington speculated back in the 1920s about subatomic energy sources, driven by the immense temperatures and pressures in the sun's core thermonuclear reactions.
And once they knew the sun was mostly hydrogen.
Russell found that in 1929. Then Hans Bay and Carl von Weizsäcker around 1938 worked out the specific nuclear reaction cycles, how hydrogen fuses into helium step by step.
Explaining how the sun could burn for billions of years.
Yes, releasing incredible energy, the sun fuses something like 650 million tons of hydrogen every second. The scale is immense, driven by core temperatures around 15-20 million degrees Celsius.
Okay, so the challenge for fusion power on Earth is achieving those temperatures, millions of degrees.
That's the core problem. You need temperatures not just of millions, but tens or even hundreds of millions of degrees Celsius to get light nuclei moving fast enough to overcome their mutual electrical repulsion and fuse.
Are there easier fuels to fuse than regular hydrogen?
Yes, using the heavier isotopes of hydrogen, deuterium H2 and tritium H3, makes fusion easier. They fuse at relatively lower temperatures, only in the tens or hundreds of millions of degrees range.
And where do we get deuterium and tritium?
Deuterium is abundant. It's naturally present in water, especially seawater, easily extractable. Enough deuterium in the oceans for potentially billions of years of energy. Tritium is radioactive and much rarer, but it can be bred from lithium, another fairly abundant element, using neutrons produced in the fusion reactor itself.
So potentially limitless fuel. What are the other advantages people talk about with fusion?
Several big ones. Vast fuel supply, as we said. Inherent safety, unlike fission, there's no possibility of a runaway chain reaction. You only have a tiny amount of fuel in the reaction chamber at any time. If confinement fails, the reaction just stops.
And the waste products.
Less problematic than fission. The main product is helium, which is harmless. There's no long-lived, high-level waste like fission produces. The reactor structure itself becomes radioactive from neutron bombardment, but this is generally expected to be shorter-lived and less difficult to handle than fission waste.
Okay, vast fuel, inherent safety, less waste. Sounds amazing.
Mm-hmm.
So what's the catch? Why aren't fusion reactors powering our cities yet?
The catch is achieving and sustaining those insane temperatures and densities for long enough to get net energy out. It's unbelievably hard.
You have to contain this super hot stuff, this plasma.
Exactly. It's a plasma gas heated so much the electrons are stripped from the atoms. You can't hold it in a material container. It would instantly melt the container and cool the plasma down, quenching the reaction.
So you need a non-material container, magnetic field.
That's been the main approach, magnetic confinement. Using powerful, complex magnetic fields to hold the charged particles of the plasma away from the walls, exploiting things like the pinch effect.
People tried simple magnetic bottles, but the plasma leaked out.
Yeah, early designs like straight tubes or simple loops were unstable. The plasma wriggled out too quickly. This led to more sophisticated, donut-shaped toroidal designs.
Like the Stellarator, invented by Spitzer, and the tokamak, pioneered by the Soviets.
Those have been the leading concepts. Tokamaks in particular showed great promise starting in the late 1960s.
Has progress been made? Are we getting closer?
Progress has been slow, difficult, and expensive, but definitely steady. A Soviet tokamak in 1969 first reached tens of millions of degrees, holding it for maybe 1/100th of a second. Since then, researchers around the world have pushed the temperature, density, and confinement time higher and higher.
What's the goal?
The goal is to reach the Lawson criterion, achieving a combination of temperature, density, and confinement time sufficient to get more energy out of the fusion reactions than the energy you put in to heat and confine the plasma. Getting to ignition or significant energy gain, we've made huge strides, huge international projects like ITER are being built, but sustained net energy fusion power is still likely decades away.
So fission is here, but has waste issues. Fusion is the dream, but incredibly hard to achieve. Is mass energy conversion the absolute end of the line for energy sources?
Well, EMAMC itself suggests the ultimate conversion, annihilating mass completely.
Which brings us to the weird world of antimatter.
Right. Predicted theoretically by Paul Dirac in 1928, he predicted that for every particle, there should be an antiparticle with the same mass but opposite charge and other quantum properties.
And they found them.
Yep. Carl Anderson discovered the positron, the anti-electron, in cosmic rays in 1932. Later, using particle accelerators, they created and detected antiprotons, 1955, antineutrons, 1956, even antinuclei like antigeuterons. Antimatter is real.
And what happens when matter meets its corresponding antimatter?
annihilation. They completely destroy each other, converting their entire combined mass into energy, mostly in the form of high-energy gamma rays, perfectly following E-MEMC-UMSOR. It's the most efficient energy release imaginable. 100% mass-to-energy conversion.
Far more efficient than fission or even fusion, which only convert a fraction of a percent of the mass.
Exactly. Which leads to some wild speculation.
Like, are there antimatter galaxies out there somewhere? Could matter-antimatter annihilation be powering some of the most energetic things we see in the universe?
Things like quasars, these incredibly luminous objects in the distant universe. It's one hypothesis. Finding large amounts of antimatter or evidence of large-scale annihilation is still elusive, though.
It really makes you think, doesn't it? This whole journey, before roughly 1900, nuclear energy was completely unknown, undreamed of.
It just wasn't part of the scientific picture at all. It was the great unknown energy source that solved the puzzle of the sun's age.
And having followed this story, understanding the nucleus, fission, fusion, even antimatter, are we sure we know all the fundamental ways energy works? Could there be something else?
Some even deeper layer. Some other fundamental interaction or energy source that we haven't even conceived of yet. It's possible. Nature has surprised us before.
Wow. What a journey we've taken, eh?
Oh.
From just wondering what stuff is made of, those early ideas of atoms.
Through puzzling over atomic weights, discovering electricity, electrons, then that shock of radioactivity.
Piecing together the nuclear atom, isotopes, realizing mass and energy are linked.
The neutron unlocking reactions, the incredible discovery of fission, and Szilard's chain reaction insight.
It's amazing how these separate threads just came together, revealing this unbelievable power source, leading to the bomb, yes, but also to nuclear reactors.
And then the completely different challenge of fusion, trying to bottle a star, tapping the power source of the sun itself, a quest that's still ongoing.
This whole story, it's really about the power of science, isn't it? Following the evidence, even when it leads to uncomfortable or unbelievable places, constantly pushing boundaries.
Unveiling these worlds within worlds, as Asimov called it. Discovering forces and energies that fundamentally changed our world and our place in the universe.
And it's not just abstract history for you listening. This story directly shapes our modern world, our energy debates, geopolitics, the technologies we rely on.
And perhaps it leaves us with this final thought to chew on. If nuclear energy, this source that dwarfs chemical energy, was totally unknown just 125 years ago, what else might be out there?
When we look at the cosmos, see things like quasars pouring out energy on scales we can barely comprehend. Could they be running on fusion, or maybe annihilation, or could it be something else entirely?
Some principle, some interaction, some form of energy conversion that is as unknown to us today as nuclear energy was in 1890. What might lie beyond fusion?